So now we'll work a few examples working with the properties of exponents. Example 1, write an expression for the volume of the figure in terms of x. And the figure itself is a cylinder, and the formula for the volume of a cylinder is given to you right here. So volume is equal to pi times radius squared times the height. And we can see here that our radius is 2x and that our height is x. So we're just going to plug those in, and then we're going to have to do a little simplifying. So we're going to go volume equals pi. Now the radius is a product of two factors. So I'm going to put that in parentheses. 2x, and we're squaring that, and then we're multiplying it by the height, which is x. So now we need to use our properties of exponents to help us simplify. So again, like I said, we have that 2x is really a product of two factors, 2 times x, and they're both being raised to the second power. So we're going to need to use the power of a product property. And power of a product here says that if you have two factors being multiplied together and then raised to a power, each factor gets that exponent. So the 2 will be squared, and so will the x. So we'll rewrite this as volume equals pi times, now 2 gets squared, and so does that x, and then I still have another x out there. Now this x, this last x, does not have a power, which means that it is to the first power. Okay, so now I know that, well, I'm going to focus on my numbers. So 2 squared is 4, and pi is pi, approximately 3.14. So I'm going to say, well, this is volume is going to equal 4 pi. Now let's talk about x squared times x to the first. Notice the bases are exactly the same. So this will be our product of powers, which was the first one. And when you have like bases, you add the powers or the exponents together. So what I'm going to do here is I'm going to add the 2 and the 1, and I'm going to get x to the third power. And there's my volume. Now they didn't give me any units. Units is usually cubed, but we're not sure what those units are right now, so we're just going to leave it. However, in example 2, it's a lot like example 1. Okay, so we have a circular component used in the manufacture of a microprocessor. That's the thing that that's like the brain of your computer. And it has a diameter of 200 millimeters and a thickness of 1/100 of a millimeter. All right, so basically you can think of this component as some type of small, teeny tiny cylinder. Okay, and it's going to look something like, there's a bad drawing, but I know that I have a diameter. Now the diameter goes through the center of the circle. It takes the entire length of that circle through the center, and that diameter is going to be 200 millimeters. And then I know that my height is going to be 1/100 of a millimeter. All right, so if I know that my diameter is 200 millimeters, well, that tells me that my radius is 100 millimeters. Now, why do I care about the radius? Because if you go back to the volume formula of a cylinder, it uses radius. All right, so we're going to go ahead and we're going to use that to help us find the volume of this circular component in the microprocessor. So we'll use volume equals pi. Now my radius is 100 millimeters, and I'm squaring that. And then I'm multiplying that by my height, which is 1/100 of a millimeter. Okay, so let's start with the fact that I have 100 millimeters squared. So whether or not you realize this in fact is a product. It's 100 times millimeters. So both 100 and millimeters get squared. So we're going to keep the pi. We're going to then have 100 squared, millimeters squared. Then I've got another 100th times millimeters. Now, why am I doing this? To kind of show you the breakdown of the units here. All right, so I'm going to start with, I think, all the numbers. So we are going to have 100 squared. Now, 100 squared is 100 times 100. So it's a 1 followed by 4 zeros. Okay, so I took care of that. Now let's multiply that by hundredths. Okay, took care of that. Now let's multiply it by pi. Now let's talk about our millimeters. All right, so millimeters squared times millimeters to the first. Well, those are like units, and I got squared and first, so I'm going to add those together because I'm using the product of powers property. So this is really millimeters cubed. Now, when all is said and done, let's see, this is 10,000 times 0.01. So really what I can do in multiplying 10,000 times 0.01 is I can move my decimal place back 2 places. Because this is really the same thing as 1 over 100, right? And 10,000 divided by 100, we're going to move our decimal 2 places backwards. We're going to end up with 100. So this is actually going to be 100 pi millimeters cubed. And that's going to be the volume of that circular component. Notice I didn't even use a calculator. All right, so scientific notation. Okay, you've learned about this in the past. And we're just going to go ahead and review it. So it's a way of writing very large or very small numbers. A number is written in scientific notation when a number between 1 and 10 is multiplied by a power of 10. And you see this a lot in your calculators, and you guys get a little bit confused by this, so I'll kind of review it in your calculator as well with you. The thing is that when we're dealing with giant numbers like these, or really, really small numbers like these, okay, the first example is a really big number, and the second example is a very small number. There are a lot of zeros, and we don't really want to work with all those zeros a lot of the time. And by not working with them a lot of the time, we can just eliminate our calculator. Don't even need to think about it. All right, so what we're going to do to work with these in scientific notation is we're going to basically get rid of those zeros by rewriting them as some power with a base 10. So we always look to the initial numbers or to the integers that you can find. Okay, so I see 45 in the front, and I need a number between 1 and 10. So I'm going to represent that 45 as 4.5. That's a number between 1 and 10. Now the question is, my decimal was originally here. How many zeros or how many spaces did I have to move it to the left to make that a 4.5? All right, so if you count, let's see, I got 3, 6, 9, 12, 15. I moved it 16 spaces to the left. So in order to make 4.5 back into this giant number, I would have to multiply it by 10 to the 16th power. So we can do the same thing with really, really small numbers. The only thing here is that this is going to end up being a negative exponent of 10. All right, so look for your integers. So I see a 2, a 3, and a 7. So I'm going to write that as a number between 1 and 10. So how about 2.37? Okay, so now the question is, how many spaces do I need to move my decimal to the right to get it between that 2 and that 3? So if you count, you're going to end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. So this will be times 10 to the negative 13. Because, so why is that one? That one usually confuses people. Because 10 to the negative 13, as we learned about with our negative exponent rule or our inverse exponent rule, that is actually 1 over 10 to the 13th power. So this is really 2.37 times 1 over 10 to the 13th power, which really is 2.37 divided by 10 to the 13th, or 1 followed by 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And wouldn't you agree that if I took 2.37 and divided it by something with 13 zeros, I would then need to move my decimal backwards 13 times to get back to this original number. So written in scientific notation, really simple. This is your final answer, and the other parts are just me showing you why that's your final answer. So we can use scientific notation to kind of make our lives easy along with our properties of exponents. So here's a couple of examples. Example 3. As of September 30th, 2023, the national debt of the United States, hundreds, thousands, millions, billions, trillions. Okay, it's like $33 trillion. And the population of the United States at that same time was estimated to be about 340 million people. So suppose the national debt is divided evenly among everyone in the U.S. How much would everyone owe? The question is, how many dollars per person are we each going to have to pay? All right, so what you're going to do is you're going to set this up really easily. You're going to take those dollars, right? According to my unit analysis here, I'm going to take the dollars that we owe, put it on top, and then take the amount of people and put it on the bottom. And then I'm going to divide them. However, we put that in our calculator, we may make a few errors. We also put that in our calculator, and you guys might not understand the final answer. So what I'm going to use here is scientific notation, and maybe I can make this a little bit easier to work with. All right, so instead of writing the $33 trillion the way that it is, I'm going to make it into scientific notation. So I'm going to do some number between 1 and 10. So how about we do 3.317 times 10. Now I need to figure out how many decimal places I moved backwards to get in between the two threes, or moved from, the end of the number in between the two threes. So I moved left, and it looks like I went 3, 6, 9, 12, 13. So this is times 10 to the 13th power. Over, all right, now that 340 million, let's see, as scientific notation could be written as 3.4 times 10, and I moved 3, 6, 8 spaces to the left. Using one of my properties of exponents here, it looks like I have like bases. Those tens are exactly the same, and then they have different powers. So looks like I'm going to use quotient of powers property. Just to remind you guys, quotient of powers, right? Same bases, you're going to subtract the exponents. So this becomes a nice easy problem, because 10 to the 13th divided by 10 to the 8th is just 10 to the 5th. So now what I'm going to have is 3.317 over 3.4 and times 10 to the 5th power. Okay, or instead of using 10 to the 5th power, 10 to the 5th power over 1, I can really take that 10 to the 5th power and multiply it by the 3.317. How about I use 3 of those 5 zeros to move my decimal 3 places to the right, so it's after the 7, and then I'll just need 2 more zeros. So 3, 3, 1, 7, and then 2 more over 3.4. Now this becomes a really, really easy problem where I'm just going to take these two numbers and divide them in my calculator. So I'm going to take the 3.317 followed by 2 zeros and divide it by 3.4. So I have $97,558.82. I don't have that much money to pay, so I don't think I'm going to be able to help you guys out. So $97,558 and about 82 cents per person. And we talked about the units to kind of figure out what we were supposed to do. I could have also been using units throughout this entire problem in numerator and denominator, but I evaluated that to begin with, so I knew that my answer would be that much per person. Example 4 is a problem from the medical or the health industry. So we are talking about the different types of cells and platelets. There is a typo you can see on the third line down. I've crossed off call and put cells there. So there are red blood cells, white blood cells, and platelets found in the human blood, and they're all generated from the same stem cells. In laboratory experiments, scientists have found that as few as 10 cells can grow into, and that's 1.2 trillion platelets in just 4 weeks. The number of white blood cells generated was 1/40th the number of platelets. And how many white blood cells were generated? Now, this is all really important life-saving information. White blood cells help with your immune system, and platelets help with injuries. So anytime that you get a cut, the platelets are the things that bind together to stop the bleeding. Now, people that get treatments like chemotherapy for cancer, or maybe they have other health issues, they might be really low in platelets and in white blood cells. So they often need transfusions. So it's important to understand when people are donating blood and plasma, how these platelets and white blood cells are generated and how quickly they can grow. As a matter of fact, I just received in the mail the other day this. I just donated blood on campus. We found out that I'm AB positive, which I already knew that. What I didn't know was that 4% of the U.S. population is type AB positive, so not very many. So what they were telling me was, well, a lot of people probably won't need my blood. However, a lot of people might need my platelets. So my platelets can go to patients of all blood types. At the very last part here, it says, you may be asked to consider donating a combination of plasma and platelet donation. So platelets are pretty important. All right, so we need to figure out 1/40th of that 1.2 trillion. All right, so what I'm going to do here is I'm going to say, all right, this is going to equal 1/40th of is multiplication, the 1.2 trillion. So I'm going to go ahead and write 1.2 trillion in scientific notation to make this a little bit easier to work with. So this will be 1.2 times 10 to what power? Well, I went 3, 6, 9, 12. And that's over 1. Now, if I use scientific notation for the 40 in the denominator, I might have a few less zeros here to work with. So let's call the 1/40, let's see. Let's do the numerators multiplied together first, which is going to give me 1.2 times 10 to the 12th. And in the denominator, let me go ahead. 40 times 1 is just 40, but let me write 40 in scientific notation. That would just be 4, or 4.0, times 10 to the first. Now I can simplify this. 10 to the 12th and 10 to the first have like bases, so I just subtract the exponents. So now I got 1.2 times 10 to the 11th over 4, and I'm just going to put the 4 over the 1.2 because those numbers I can easily divide. What's 12 divided by 4? It's 3. So what's 1.2 divided by 4? It's 0.3, or 0.3 times 10 to the 11th. So now what I can do is I can take that 0.3 and move the decimal place over 11 spaces. So I'll have 3 followed by 10 zeros. All right, let's see, hundreds, thousands, so we're at 30 billion and 30 billion white blood cells. Now, some of you are saying, why would I do all that work when I could just put this into my calculator? Okay, let me show you this. So we're going to take the 1.2 trillion and we're going to divide it by 40, and let's see what we get. So I'll take 1.2 trillion, which is 1, 2, 2 zeros, and then I think I have 9 more. And I'm going to divide that by that 40. Oh, look what I got. half the time you guys see this and you have no idea what it even is. This is scientific notation. This is 3 times 10 to the 10th power. Now they use an E, and I'm not sure exactly what they're using that E for, but that's to tell you that this is 3 times 10, and then this number 10 here is what power 10 is being raised to. So 3 times 10 to the 10th power ends up giving us that 30 billion white blood cells that we got right here.